and remainder theorem. We want our students to remember that if a polynomial, let's say p of x equals 3x to the third plus 2x minus 4, remainder of this p of x over x plus 2 is p of negative 2. So if I want to find the remainder of p of x over x plus 2, and I don't care about the quotient, I only want to find the remainder, all I have to do is, remember this is negative 2, in other words, x minus negative 2. This is the so-called a, x minus a. So this is the remainder, whatever that is. Also, why is this so important is that if p of negative 2 is 0, if it happens to be 0, then x plus 2 is a factor of p of x. Is it? I don't know. I didn't calculate. I just made up a problem. We will calculate right now. I highly recommend don't plug in stuff in the calculator. Always create the function, put the function in there. A function in my case that I just picked is this. You see it, you make sure that this is correct, correctly entered, and then you just go to second and table and you plug in negative 2. If I click enter and I get 0, then I know the remainder is 0, which makes x plus 2 a factor. If I get any other number, I will say no, x plus 2 is not a factor of the polynomial p of x because the remainder is not 0. So let's see. I got negative 32. So I will say, in this case, p of negative 2 equals negative 32. Therefore, x plus 2 is not a factor of p of x. This is very important for Calc 1 when you will see when we calculate limits. Very important topic to remember. If I plug in a number in a polynomial and I get 0, then x minus that number is a factor of that polynomial. Very important concept for limits in next semester. Now, if I have p of x and I have x minus 1, then p of 1 is the remainder. If the remainder is 0, then x minus 1 is a factor of p of x. So the remainder theorem says plug in the polynomial negative 2 to find the remainder. If it happens that the remainder is 0, then you're concluding that x plus 2 is a factor. If the remainder is not 0, then you cannot conclude that it's a factor. You can only conclude that it's not a factor. So this is an important topic. Not as important as this one. Can you live without this? Yes. But it's very important to remember, though. That's it. So the question will be, is this, you don't have to use the factor of the remainder theorem, but it's wise to. I will ask, this is a polynomial. Is x plus 2 a factor of this polynomial? You can use a long division or synthetic division. It will take you 10 minutes. But if you simply plug in negative 2 and you get negative 32, you'll say no, it's not. If you simply plug in -2, as we just did with the calculator, and get 0, you will say, yes, yes, it is a factor, because the remainder is 0. Good. Next question. What is our next?
Can we do?
Yes?
Can we do composite functions?
Excellent. Yes. Yes. In the next class, it is very important to understand that when we look at, for example, the square root of 2x plus 1, we have to understand that this is the outer function, and this is the inner. Without this understanding, the inner and the outer, and there is more than one option, of course, but the inner is 2x plus 1, and the outer is the square root of x. So if we want to decompose this, I would say that this equals f comma g of x. This must be the inner. If you want it the closest to x, that's what the g of x is. And when I'm done and I find a number for this, which function I apply to this number? I apply the square root of x. So then f of x equals the square root of x. And this function composition with this g and this f is this. Now, this is very important. Now I can ask this situation, also easy. Let's say f of x equals 1 over x, and I'm given g of x equals x squared plus 2x minus 3. And I'm asking you to find g comp f. You have to write the definition, g of f of x. You replace this by 1 over x. And now you know how to proceed. 1 over x, everything squared. 2 times 1 over x minus 3. This is the function composition of these two functions. In this particular order, f is first, g second. That's why I replace f and I plug in g. Everywhere I see whatever squared plus 2, whatever minus 3, whatever squared plus 2 times whatever minus 3, that's the function composition. Now, if I ask you decompose this, it's hard. I'm not going to ask you to decompose this because this is not the point. The point is to be able to decompose this. Can anyone give us the inner for this and the outer?
The inner will be 2x plus 3. And then the outer will be 1 over x.
That's it. Thank you so much. This is it. No one will ask you to decompose this. There is no need for this. Because in Calc 1, you will see it's very easy to find what you need from this format. But if you don't understand what this means, what is the inner, what is the outer, it may be more difficult. Although, I have to say that for this particular case, you can replace it by 2x plus 3 to negative 1. But you still have to understand the inner and the outer to be able to continue from here in Calc 1. Okay, good. Next question. Anything else you would like to continue with? Was anything else from the test, maybe?
Can you do an exponential equation?
Yes. Here they are. We don't have to choose these. We can go back to the book. I consider this one the most difficult type of exponential equation.
And I guess do that one.
Okay. Why I consider the most difficult is because students have difficulties in factoring and simplifying and moving terms around. I don't understand why, but it happens. So 2 to x plus 1 equals 5 to 1 minus 2x. Well, if I had the situation, let's say 1 over 8 to x plus 1 equals, let's say, 4 to the 3x, I would say piece of cake, because both can be presented with the same base. This one can be replaced by 2 squared, and this one can be replaced by 2 to negative 3. No need to apply log here. Can I? Yes. But I wouldn't. This can be replaced by 2 to negative 3. This can be replaced by 2 squared, and I'm done. It's just going to be very straightforward, right? It's 2 to negative 3x minus 3 equals 2 to 6x. Exactly based on the same principle, we looked at this, same principle. Log of this has to equal log of this. These two numbers have to be the same. Same principle, one-to-one property, same principle, this has to equal that. I will never apply log, it's a waste of time. So negative 3x minus 3 equals 6x, and I take it from there. So negative 3 equals 9x, x equals negative 1/3. Done. Don't apply log here as long as you notice that both can be presented with the same base. But here my hands are tied. 2 and 5 can never, ever be presented with the same base. So here I have no choice. And I have to apply natural log to both sides. There is no other way. I need to apply the inverse function. What is the inverse function of an exponential? Is log. So now I have to bring this in front as a factor, meaning if you don't put parentheses, the whole thing collapses, times natural log 2. The same thing with 1 minus 2x. If you don't put parentheses, the whole thing collapses. Now, if I don't notice that I have to distribute and then separate the terms with x, put them all on one side and terms without x on the other, I get stuck. And no, I don't want you to evaluate this. You can say, but this is a poor number. Yes, but I don't want to build up the error in the equation. So I will calculate if I need to only at the very end, but I have to distribute. So x natural log 2 plus natural log 2 equals natural log 5 minus 2x natural log 5. Now this term and this term belong to the same side. This one belongs to the other. So I have x natural log 2 plus 2x natural log 5 equals natural log 5 minus natural log 2. Of course, I cannot combine these. But if I can combine and I'm solving for x, what should I do? What do we do when we cannot combine, but we have to solve? How is it called? Can anyone help? What do we do? When they're not like terms, but I still have to solve for x, what is my option now?
Factor of the x.
Thank you very much. natural log 2 plus 2 natural log 5 equals natural log 5 minus natural log 2. Final answer. How do I get this? What will be the last step here? Unless I want to approximate. What do we do now? Please? Anyone? Can anyone help, please?
Divide.
Correct. Natural log 5 minus natural log 2 over the number that multiplies x. Natural log 2 plus 2 natural log 5. Indeed. Perfect. Good. Next topic, please.
Can you put that previous page?
Of course.
Thank you.
Thank you. Okay. Yes, okay.
Yes, thank you.
Thank you. Good. The next topic, please. Let's choose. Let's choose, please. Yes.
Can you do no, examples for number 5?
Yes, for number 5. What is number 5? The graph of a rational function.
Okay.
This one?
Yes.
Perfect. Good pick. Page 9. So here's an example. Let's say x minus 2. Let's put a 2 in front. And x squared minus 4x plus 4. Okay, so what do you think would be the first step? We're asked to graph. What will you do first?
Factor the denominator.
Absolutely. Can anyone factor the denominator for us?
X minus 2, x plus 2.
Careful, it's a trinomial.
X minus 2 squared.
Excellent. Good. And you will immediately state that x does not equal 2. And you will simplify and get 2 over x minus 2. The factor still stays, so x equals 2 must be a vertical asymptote. Do you all agree with that so far? Yes? No? And then I start the table. And I have negative infinity, I have 0, I have 2, and I have infinity. I plug in 0, and I get negative 1. It's type 2, which means 0 and 0. Y equals 0, horizontal asymptote. And I need to find what happens left and right. with 1.9, I don't put them in the table, and with 2.1. I know it's infinities because it's a VA, vertical asymptote, but I need the sign. Can anyone identify the sign plugging in 1.9 and identify the sign plugging in 2.1? And that's all I need. There is nothing else other than symmetry, but obviously it's not symmetry. Can anyone give us the sign? Left and right.
Negative, positive.
Yes, indeed. So, first we graph the asymptotes. Here they are. This is an overkill because it's already there. But I have to graph x equals 2. And now I'm ready to graph the function. From approaching 0, crossing at 0, -1, going towards the asymptote, approaching asymptotically towards -infinity. Done. On the other side, it's coming from positive infinity, approaching 0 eventually. And this is f of x, 2, x minus 2 over x squared minus 4x plus 1. This is it. Now, what happens if I have a situation in which I have x minus 1, let's say, and then I have x squared minus 2x plus 3. Minus 2x minus 3. I just want to show what happens when a factor disappears completely and the factor that goes away is a hole in the graph and the other one is a vertical asymptote. So I just want my denominator to, let's say, be factorable into x minus 3 and x minus, and x, I can change that. So x squared minus, so x squared Charles, you are coming in through 2 different devices. Okay, so x squared plus x minus 3x is this, and -3 times 1. So this was my function, x squared minus 2x minus 3, the numerator is x plus 1. I factor the denominator and I do this. Do not, before you write this, you cannot simplify before you write the restriction. You write the restriction and then you simplify. And of course, x cannot be 3. So the simplified form of this function is, or expression is 1 over x minus 3. X equals 3 will stay as a vertical asymptote. But at -1, this will become a hole in the graph. Why? Because the factor disappeared completely. Here is not the same situation. It was the same factor, but it was still left in the problem or in the simplified form. Therefore, this is a vertical asymptote.